Welcome back to your physics notes. So what we're going to talk about today are some examples of the first, second, and third laws, some gotchas, and some conceptual examples. So first law, conceptual examples. So one of the most common things you will see on the AP exam or in kind of a classic physics problem is you will see a frictionless surface. Okay. Now, it's pretty difficult to make frictionless surface. In fact, it's kind of impossible. But hey, we can always imagine that they exist. So an example of how Newton's first law might be, your understanding might be tested, is if we tell you that this thing has a velocity to the right, this is a block on a frictionless surface, what would it do? And the example is it'll keep doing the exact same thing that it is doing, which is moving to the right with velocity v until some net force acts on it. As long as the net force is zero, it will just maintain its motion. Now, remember that its motion is a vector, and vectors are straight lines. So if we jump down here to gotchas, you can think about the things that we talked about in class. Or so we had the pendulum problem where the rope disappeared. What would the path be? We had a pellet going through a tube, and when it came out the tube, what would the path be? You can also have something like a slide, okay? So if this is Jimmy and he's about to go down this slide, it's a water slide or something like that, what would his path be at the end? Well, you could make up some crazy stuff with this, but he would come off of it going in a straight line. So you might think he would continue in a straight line. And if for some reason this dotted line represented a magical boundary where once you crossed it there was no gravity, you would keep going in a straight line until some force acted on you. But on Earth, he will move with a constantly changing vector that is constantly changing towards the direction of the net force, which in this case, the force providing that would be his weight. Okay, so his horizontal component of this vector won't change. He'll keep moving to the right with a constant velocity in the x dimension, but he'll be adding velocity in the negative y or downward direction. So this vector, he'll speed up until he hits the ground. Now, second law, conceptual examples. Conceptually, I might ask you something like, if you double the net force on an object, how does that affect its acceleration? Well, I refer you back to this, which is my favorite way of writing Newton's second law to think about, and you can see the proportionality here. If I double the net force, I will double the acceleration. Whereas if I double the mass, I will cut the acceleration in half. If I cut the mass in half, then I'll double the acceleration. So you want to be able to think about Newton's second law in those terms for conceptual type problems. Now, gotchas with Newton's second law would be, the most obvious one is you don't think about dimensions. If you forget about dimensions, you will make a very common error. For example, I tell you that there's a block. Let's say it's a blob. There's a blob that's out in space, okay? There is a force acting on the blob in that dimension. Let's say gravity. Gravity's pulling in that dimension towards another blob out in space. But there's also a force acting in this dimension. Let's call that F1. Call that F2, okay? And whatever this force is, let's say the blob has a little rocket pack on the back, okay? So it's shooting off some gases. Those gases are pushed that way, so they push the blob forward in that direction. And I ask you, what will the acceleration of this be if you know that the magnitude of F1 and F2 are the same? And you might want to tell me, well, they'll be 0 or they'll be 2F. They'll just double, and that's not actually true. You got to think about the dimensions, okay? If you have one vector, which is F2, and you have another vector, which is F1, you add those mathematically by putting them head to tail, and you think about what the net result is, which is the hypotenuse of this triangle. Okay, so if you just add them or you just subtract them, the magnitudes, you're going to do it wrong. Instead, you have to do it mathematically, where you make a right triangle and you find the hypotenuse. So to do that, if you think about it, use Pythagorean's theorem, where let's call this A, that B, and the hypotenuse C. And Pythagorean theorem says that A squared plus B squared equals c squared. So c would be the square root of a squared plus b squared. So that would be the net force acting on it. It would be the square root of F1 squared plus F2 squared. That would be the net force, not just 2F. So that's a very common gotcha. Now, application runs along those exact same lines. What you'll need to do is, let's say there is a block and it was given some initial velocity v. It's moving along a frictionless surface. And let's say there's a rope attached to it that is pulling with a force T. So what you would do is you draw a free body diagram. You have the weight of the block. I tell you it has a mass m. You have the normal force. And how do you apply Newton's second law? Well, the first thing you have to do is you have to define your axes, your dimensions. I'm going to say this is positive x, this is positive y. And Newton's second law involves vectors. So that means that I would write Newton's second law for the x dimension. That's equal to mass times acceleration in the x dimension. And I would write Newton's second law for the y dimension. Okay, so if I look at my forces in the, let's start with the x dimension. I told you this was frictionless, so there's only one force, and that's that force T. So the sum of my forces is just the forces in the x dimension, which is only T. So I could write T equals m times whatever my acceleration in the x dimension is. And I could solve for that acceleration if I wanted to. It would be T divided by m. Now, I could do the same thing in the y dimension, but you notice now I have two forces, and you have to ask yourself, this is another conceptual question, what is the object doing? I described it as moving to the right. You can see that it will accelerate to the right because T results in an acceleration. But in the y dimension, it's not moving up or down, so we know that there is no acceleration in the y dimension, so there must be no net force in the y dimension, which means that A is 0 in the y dimension, which means that the sum of the forces equals 0. And if I now plug in my forces, I said that up was positive y, so I could say n minus mg, because it's in the opposite direction, equals 0. So n equals mg. So now I have only one acceleration. It's in the x dimension. That acceleration is equal to t over m. And I have no acceleration in the y dimension, but I know information from this. I know that the normal force is equal to the weight in this example. Now, third law, conceptual examples. They could ask you all kinds of complicated stuff involving objects pushing on other objects. The most complicated one that you usually see on the AP exam is if you have a block on top of another block. And let's say there's a rope here that's pulling this block. Well, there's going to be a certain amount of force, let's call that M1, let's call that M2, where you can pull these and there'll be friction on M1 between it and the surface. But as you pull this, if you pull at the right speed, the right amount of force, you could get M2 to slide along with M1. Static friction be enough to maintain that contact. Well, there would be a force on M1, on M2, causing it to accelerate. That would be the friction. Well, and if there's friction on M2 from M1, you know that there must be additional friction on M1 that's equal and opposite. So that's an example of an action-reaction pair. Another one that they like to ask a lot is, let's say you have a table, and on that table is a box. And you tell me, well, you draw a free body diagram. There's the weight, mg. There's the normal force. Those are the only forces acting on it. But the question is, what is the reaction force to the weight? And the most common answer is the normal force, because you see it right there, but that's not right. A reaction-action pairs come from the two objects that the forces are coming from. And what you have to ask yourself is, what object causes the weight? And the answer is the Earth's mass. So the Earth's mass pulls down on the box, and the box pulls up on the Earth. So the reaction to that is the box pulling up on the Earth. It's a very common question, and you should always be able to identify the two objects involved in a force relationship. So third law gotchas, that would probably be the biggest one, would be that right there. Another one would be the classic horse and buggy problem. So let's say you have a buggy. That's an ugly buggy, but hey, it works. And you have a horse. This is probably going to be even worse horse. That's a horse. Now, the question that people like to ask is, they state Newton's third law. If the buggy pulls on the horse in an equal and opposite fashion than the horse pulls on the buggy, then the buggy can't move. And that seems like a very slippery slope that you would fall down and say, yeah, what do you mean? Third law can't be right. But in fact, you have to remember that the forces in an action-reaction pair act on two different objects. Okay? So as the force pulls on the buggy, yes, the buggy pulls back. So this is the force of the horse, H, on the buggy, HB. This would be the force of the buggy on the horse. They're the exact same thing in opposite directions. So if you look at this, you might say, well, they can't pull each other, they cancel each other out, and that's not true. If you look at the forces acting on the horse, there's also friction between his hooves and the earth, and they prevent him from sliding backwards, so they actually propel him forward. That's how you walk. If you try to walk on ice, it's more difficult. Friction between the wheels and the earth is significantly different because there's no real sliding going on. This doesn't slide either, but these are on axes, so it's a lot less. So you have a different amount of friction. And the friction there actually makes the wheels rotate rather than slowing down the buggy. So this is a very common misconception. And if you think, well, action-reaction force pairs must always cancel each other out, that's not true. They act on different objects, so they do not cancel each other out. All right, that's it. Those are an overview. You will spend a lot more time, especially with Newton's second law. I know that was quick, but that's a broad overview for your notes. Thank you.